Cryptool demonstration. Now, Cryptool is a program you can download from www.cryptool.org, cryptool.org. Now, when you first start up Cryptool, there's usually some sort of sample or instructional text here. Now, I've gone ahead and opened up a separate text file here, and I've just gone and grabbed the Gettysburg Address just to have some sample text to work with. Now, Cryptool gives you several tools to experiment with cryptography, trying different encryption and decryption methods, trying different cryptanalysis methods. So, for example, here I've got my Gettysburg Address, and one of the tools that we mentioned in the cryptography domain was a basic Caesar cipher. In other words, shifting the letters a certain number of characters. So as we open this up, you see it says select your variant. You can do a Caesar, and what are you going to shift it over as? So we could say, so notice right now A to A. We could say, how about A to D? And so you see A becomes D, B becomes E, and so on down the line. We could also do a rot 13 if you want, rotate 13. We could just pick a certain number value if you wanted to use that as our how many spaces to rotate over, just like we talked about here. Now, truthfully, sure, this is easy to figure out, and you wouldn't need the Cryptool to decrypt this. But the point is to show what we can do with the tools. So let's encrypt it, and here's our encrypted text. Now, if you look, there's quite a few letters that tend to show up quite often here. You'll notice Z shows up often here. S, not too bad. If we look through, we can see some. Let's see, U probably shows up. Oh, there's quite a few U's. Okay. So when we do analysis of a cipher, and in this case, so here's our cipher text. I'm going to go ahead and just minimize our original plain text. We don't need it at the moment. So here's our cipher text of the Gettysburg Address. Now we know what it is. Let's say this was captured ciphertext, and we have no idea what it is. One of the things that we can do is we can analyze this. Now, this particular set of tools, if I had a guess as to what type of encryption it was, it would make it very easy. See, I could say I have ciphertext, and I'm guessing it's a Caesar cipher. So the first thing it takes a look at is, you notice that it checks for frequencies of letters. You'll see, so we get a nice little histogram of how frequent certain letters appear. This is the letters within the encryption there. All right. So it compares it with a reference file called english.txt. In this case, it's comparing this frequency with the frequency of letters in the English language, and then saying, oh, well, then the most frequent one is probably this letter. See, so we'll take a look here. And then it does a quick analysis of how the positions. In other words, where the letters often occur. Again, this is analyzing the ciphertext. And then it comes out and says the derived key is C. For a key offset of 0, the key is D. Okay, so because of that, it has to check and see what the key offset. So it says there's 2 keys possible because we did a little key offset. So we'll try having it decrypt with C. And what we get with, see, so D with a key offset of 1, 7 years ago. All right, now, I did not expect anyone to look at that and suddenly go, oh yeah, that made complete sense that that's how they did the analyzation. But you can kind of get an idea of what they're doing here, is they're working on frequencies. So as we get into more complex ciphers, that's exactly what we do. So let's back this up a little bit here. We're just going to close up some of these windows. Here's our cipher text. Let's go take a look at our original plain text. Let's try a different encryption. So this time, you can see I've got AES encryption. So now in AES, I would need to pick a cipher, a key to use using hexadecimal characters. So I could do 00, I could do 01, 02, 03, 04, which would not be a good idea in the real world. 06, 07, 08, 09, 10, all right, 1. Let's see, then we'll do 0A. Actually, we should do 0A here. Let's do it that way. 0A, 0B, 0C, 0D, 0D, 0E, 0F. There we go. Alright, so that gives us all our values from 0 through F. And let's encrypt it that way. And this is what we get back. So this is our ciphertext now of the Gettysburg Address. And again, because we have the original plain text behind us, it's easy to figure out. Let me just minimize this for a moment here. And let's say you were trying, this is actually the text we'd see. Now you'll see dots in certain spots. Those dots are the representation of the hexadecimal here. See, so some of them cannot be represented in just standard ASCII on the screen. Alright, see, so C2, AA, 1A, these don't have any particular setup with it. C3, 02. See, so this is all the hexadecimal values for every character going through that. So now if we wanted to analyze this, so you'll notice we've got our symmetric encryption and run null. And it says, alright, the search space can be limited to reduce search time. So in other words, if we know which keys to search, alright, followed by an unknown byte, we can see which is going to try to derive the key. Now if you'll notice, we've got all different options for automatic analysis. This is all specifically for our symmetric encryption. We're going to be fine without changing any of these right now. So let's go ahead and try a start. And now look what you see right here. 3.1e to the 25th power e years to do a brute force analysis of Rheindahl. Because there's so many layers of not knowing any cipher key at all. Alright, so many layers of encryption, so many rounds of substitution and transposition, so many rounds of diffusion and confusion, that it takes that long. And this is a fairly hefty PC that we're working on at the moment here. But it's still going to take that many years just to try to crack this here. Remember, we said any encryption can eventually be cracked. It's a matter of making it too expensive, too costly either in processing power or in time to make it worth the effort. If this was an urgent message that I needed to crack, 3 years, 3.1e raised to the 25th power years is not going to be worth it. So I'm going to cancel this for a moment. And you'll see these were some of the results as it tried the different keys as it went through. And you can see it kept trying various keys. It's literally just brute forcing through every possible key that was available, starting and working its way down through. Alright, so only the first couple characters were decrypted to try to figure it out. You can see it hasn't even come close yet. Okay. So in the real world, we've shown that it could take quite a bit of time here. Now there are other methods besides just brute force. Perhaps if we know a piece of the key, or if we know something important to a particular person there, that might give us a way why it's so important to choose random keys rather than keys that have some meaning. I could give it a try if you had used a certain word. Or in this case, if I know part of the key, let's try this then here. So let's see what happens when we do know part of the key. We'll do our analysis. We'll look at symmetric encryption, and we just happen to know it's the Rheindahl cipher. See, that's the hard part too, just figuring out how it was encrypted. And we'll start with our 00, 01, 02, 03, 04, 05, 06, 07, 08, 09, 0A, 0B, 0C, 0D, 0E. Oh, no. Let's say we just know up that part. We don't know the tail. Let's give it a shot. And look at that. In just a few moments here, it's come up with all the different values. Now we can look at it and see, wow, that looks like... See, and let's expand this a little bit so we can see. Make it a little bit smaller here. There we go. If you look at our window, see, it started with 0F. Alright, 0, all the different values for the last 4 that we could have had. And you'll see 4 scored and 7 years ago. That looks like it. So we'll say go ahead and accept that selection, and it's now decrypted the text for us.